So part of electrochemistry is knowing the strength of reducing agents, oxidizing agents, and what do we use as our guide to predict strength of reducing agents and oxidizing agents? Thermochemistry, thermodynamics. And what do you have in electrochemistry as your guide of thermodynamics? It starts with the word P. We might say standard reduction potential. Yeah, reading a voltage. So this thing here is our standard reduction potentials, and so that voltage is a measure of thermodynamics, or like free energy, and we use it to make a prediction about the strengths and weaknesses of oxidizing agents and reducing agents. Which side is the oxidizing agents? Correct. So these are all oxidizing agents. Oxidizing agents get reduced. And how do they get reduced? Well, when they oxidize something, they take electrons away. So where are the reducing agents? Right, all these species over here, we say they're in their reduced form. Here's the oxidized form. So for this question here, we need to look at our table of half reactions. Unfortunately, not every species in this question was on that, so I have to write these out for us. And I'm going to dispense with writing aqueous. Well, here we have some solids. That's mainly the whole reason I put it up. It's not going to be important. The important is that oxidizing agents over here, reducing agents over here, and what we learned last time about what makes one stronger than the other. So I kind of wrote these in most negative, most positive. You won't always get them that way. On the little table on the practice quiz, they're almost in order. And in fact, this is upside down from what we saw in the lecture. So here we have the most positive, most negative, and what I have written on the board right now, we have the most negative, most positive. So we want to go back to what we learned Friday. The most negative reduction potential, the species that's in its reduced form, that's the strongest reducing agent. The thing with the highest positive reduction potential when it's in its oxidized form is the strongest oxidizing agent. So right here we can say something like these are all oxidizing. And going down this way we can use this adjective. So these are all in their oxidized form. And up here we have reducing agent. So increasing in strength, increasing in strength. All right, so that should give us everything we need to answer this question. Right, this is the most positive. Now, is there any that when you see this on an exam, you can just immediately get rid of? I'd say these two, they're in their reduced form. But let's do this. Am I lazy or am I efficient? So this is on your practice quiz, and I went over it. And sometimes every other year, I just change this word, and it changes the answer. Well, I'll have to try that again later. Yeah, one of the solids. Looks like this one. Now, we don't necessarily have to have solids over here. Here's tin 2 is a reducing agent. Iron 2 is a reducing agent, because it can go to the iron 3. So reducing agents here, oxidizing agents over there. Any questions on this concept? So typically at the beginning of lecture I ask, are there any questions? I didn't do that today. Are there any questions? And I come prepared. If there's no questions, I make up my own question. I gotta quit rattling paper. It makes for lots of distracting noise. So this is a favorite type question for me for a variety of reasons. It says, consider the half reaction where sulfite is converted to sulfate. Are electrons a reactant or product? Is this process a oxidation or reduction? And how many electrons are involved in this process? All good things. I think when we answer one question, we've answered the other. Are electrons a reactant or a product? Does that answer this question here? Is this process an oxidation or reduction? Half reaction? What do you think? So if a reduction occurs, are electrons reactant or product? Leo goes GERS, right? Gain electrons, reduce. So for it to gain electrons, electrons would have to be a reactant. Leo loses electrons, oxidation. So oxidation, if an oxidation process occurs, electrons show up as products. When a reduction occurs, electrons are reactants. Good stuff to know. There's possibly, so that's all good. How many electrons are required in this process? Probably something you've never seen until today. And maybe at the beginning I said, oh, the method of half reactions is so wonderful because we can balance things that would just be too difficult to balance by inspection. It also answers a lot of these questions. We can start out and use the method of half reactions, and that algorithm will put electrons on one side or the other. We don't even have to think about it. Well, we might have to think balancing charge, right? So that's what we're going to use to solve this problem, is the method of half reactions. There's one last reason why this is a favorite question of mine, and it starts with the letter N. What do you think that word is? What? Nomenclature, yeah, naming. What is sulfate? What is sulfite? If you don't know, you're in trouble, right? All right, I got sulfate memorized as SO4 2-. Sulfite's got to have one less oxygen. Nature wasn't kind because sulfate and sulfite have the same charge. All right, so you miss this, you might miss up the rest of this. All right, so I'm gonna start out with where sulfite, SO3 2-, gets converted to SO4 2-. So there's half the battle. All right, now we pull out our algorithm for the method of balancing half reactions, and we say something like balance elements other than hydrogen and oxygen. All right, so then what do we do next? Which element? Water. Yeah, we balance oxygen. Got 4 oxygens over here, 3 over here. So as Caden said, we balance oxygen by adding water. Now we have to balance hydrogen by adding protons. All right, now we get to figure out whether this is an oxidation or a reduction, whether electrons are reactant or product. I got -2 over here. I got 0 over here. Where do I add the electrons and how many do I add? Very good. Yeah, so now I have -2 over here. I have -2 over here. We've balanced charged. The elements are balanced. And now we can answer this question here. All right, is this process a reduction or oxidation? Loses electrons, oxidized. How many electrons are required for this process? 2 electrons. Is there any other points to make about this? Oh, yes, you want bonus information. In OChem, we haven't gotten to it yet, but we can talk about oxidation reduction in terms of like hydrogen or oxygen. An increase in the oxygen content on a molecule typically implies oxidation. So this has 3 oxygens, this has 4. So I can look at this and I don't need any of this. I can say you oxidize sulfite, you'll get sulfate. You oxidize sulfate, you'll get persulfate, which is SO5 2-. So a little bonus chemistry information there. Absolutely. Yay, Caden, I'm gonna go there now. How embarrassing. All right. Combustion reaction. What is the reducing agent? What is the oxidizing agent? We could do half reactions. We could do try and determine the oxidation states. Let's stick with oxidation states. Here oxygen has a -2 charge. Here it has a -2 charge. Was oxygen oxidized or reduced? Oxygen got reduced. So we're going to say, maybe here's something like this. Let me spell right. Oxidizing agents get reduced. We can say oxygen is the oxidizing agent because it was reduced. Here's a bonus. You get some OChem today. CH4 is methane. Only I weaseled my way out, but it answers Caden's astute observation. We can look at oxygen and see that its oxidation state went from 0 to -2, so it went left on the number line. It had a decrease in oxidation state. It went from 0 to -2. That's moving left on the number line. Methane, well, I weaseled out. I didn't want to calculate oxidation states of carbon because it's sometimes difficult and not worthwhile. But I can say methane is the reducing agent. If I really want to weasel out, I'll say it has to be because oxygen's the oxidizing agent. But we can say methane is the reducing agent because carbon lost hydrogen and it gained oxygen. Remember what we said up here? If I oxidize sulfite, I get sulfate because the oxygen content increases. I could also look at this here and say oxygen here and oxygen here. It's gained hydrogen. The inverse of this down here. Any questions? So here's our nice table, and it could get flipped like our first example. All right, it's not where I wanted to go. So here's what we went over this morning with, here's what we went over with our example problem. Strongest oxidizing agent, strongest reducing agent. Reducing agents have to be in their reduced form. Oxidizing agents have to be in their oxidized form. So the more positive the standard reduction potential, the stronger the species on the left in the half reaction, the reactant. The more negative the standard reduction potential, the stronger the reducing agent, that product on the right, the thing that's in its reduced form. So I've referred to the table of standard reduction potentials as a measure of perhaps free energy. And it says here, delta G for a redox reaction can be found by using this equation here. What's going on here? Where N is the number of moles electrons transferred. And for the sulfite to sulfate, we found out this morning that was 2 electrons. F, to memorialize Michael Faraday. Have you heard of him? Now that I'm into these videos, I want to do a little Wikipedia bio on him right during lecture. Make things more interesting, maybe next time. Well, he found a way to relate amount of electrons to a mole, coulombs per mole. And here's some different units. Now, unfortunately, this slide is not telling us what E is. Oh, that's all right. E is the standard cell potential. Let's make a battery out of copper, chromium, and the appropriate salts. Those are going to be in solution. So possibly what we need is our half reaction data. So from last week in lab, you can straight up calculate this right out, right? You're going to say, oh yeah, this E cell was equal to a reduction potential minus a reduction potential. Typically, I like to write in this cathode, anode, reduction, oxidation, all these things, but we only got 5 minutes, so we don't have time for that if I'm going to get all the way to this thing here. So I'm going to just call names and make people feel uncomfortable. Glad you said that loud enough for the tape to get it. I need students' comments to make an exciting a video. Well, you knew that the voltage has to come out positive, right? Oh, hey, I'm so sorry. It shouldn't change anything, though. Just seeing if you remembered what happened in lab last week. You might say on that handout, we used 0.36, but we're not going to go there. Right, we want the most positive one here and the most negative one here. All right, so this is one I can handle without my calculator, possibly. What is E cell? The standard. This is the voltage our battery would put out. All right, now if we're going to use this equation, we got to figure out what N is. Almost. You did this in the problem set. And I'm going to come up here and say, well, this means that chromium is going to go to chromium 3 plus and give us 3 electrons. And I'm going to change the voltage there. And that means copper's going to do its usual thing. So to add these together, I need to get the number of electrons the same on each side. So I'm going to multiply this by 3, this one by 2, and I leave those alone. So 3 copper, 2 pluses, and 2 chromiums turn into that many chromium plus 3 coppers. And I can just sum these up. So 2 reasons why I wanted to go to this thing today is students sometimes want to mix this process and this process together, and you don't want to do that. When you use this equation, you just use these as they're given in the table. If you don't have this equation, you rearrange these and add them together, and you'll either get a negative voltage or a positive, depending on which way you write it. But there we go. So now I think we might be able to answer this question quickly before we run out of time. Negative what? I think this is a 6 electron process. All right, the Faraday constant, 96,485. And what I really wanted is the correct joules. Well, a joule volt per mole. We got moles here. That's dandy. And then finally, so in lab I told students, this is a little different. Enthalpy, we changed the sign. If we multiplied, we had to multiply our equilibrium constants. We had to do the reciprocal. If we multiplied, we raised to the power. Here with this, if you take 2 half reactions and rearrange them so you can get an overall electrochemical reaction, you leave the voltages alone. But how does that enter into delta G right here with the N? Can I borrow your calculator? Thank you. I'd dig it around for mine in my briefcase, but all right, 108 times 96,485 times 6 equals, that looks like a lot. I'm going to divide by 1,000. Thank you, Caden. The -6, let me bring this up. I cheated. I had to pull this up. There's the negative. And the cell potential is positive. So that's where the negative comes. Good question. Any questions? I went over. I'm sorry. Wanted to make sure you got your money's worth. But we calculate the Faraday in lab Wednesday. So we'll do an example problem Wednesday using the Faraday and electrolysis. No, we don't. It's simpler than that. Actually, you measure volume of hydrogen gas. It's almost like the very first lab. You make hydrogen gas from electrolysis, figure out moles of hydrogen, figure out moles of electrons, and you monitor current. You know the amps and time. You get some physics. Good time coming up. You're welcome. See you all Wednesday.